Welcome. Today, we're breaking down what GPT really means and how these models actually work. The acronym GPT stands for Generative Pre-trained Transformer. Generative is straightforward. The system is designed to create new text. Pre-trained means the model first learns patterns from massive datasets and can then be fine-tuned for specialized tasks. And Transformer. That's the key. It's the neural network architecture at the very heart of today's AI revolution. The goal of this video is to give you a clear, step-by-step, visually guided explanation of what happens inside a transformer. Transformers power all sorts of AI systems. Some turn speech into text. Others generate speech from text. And image generators like DALL-E or Midjourney, which amazed the world in 2002, translate written descriptions into images. The very first transformer, introduced by Google in 2017, was built for machine translation. But the version we'll focus on here is the one behind tools like ChatGPT, trained to process text, sometimes paired with images or audio, and predict what comes next. Here's the trick. The model predicts the next word by producing a probability distribution of possible continuations. At first glance, predicting a single word might sound different from generating full passages, but it's the same process. By predicting, sampling, and appending results over and over, the model builds entire paragraphs. Scaling this idea up from GPT-2 to GPT-3 showed just how powerful it is. Suddenly, the outputs weren't random snippets, but coherent, context-aware stories. When you interact with ChatGPT, you're actually watching this prediction process unfold, one word at a time. And honestly, it would be fascinating to see the full probability distribution behind each choice. So how does data move through a transformer? The input text is broken into tokens. These can be words, subwords, or even characters. For images or audio, tokens represent small chunks or patches. Each token is mapped to a vector, a list of numbers that captures meaning. Similar words get vectors that sit close together in this high-dimensional space. These vectors flow into an attention block, where tokens interact and adjust their meaning based on context. For example, the word model means something very different in machine learning model versus fashion model. Next, they pass through a feed-forward layer, a kind of neural transformation applied independently to each token. This alternation, attention, then feed-forward, happens multiple times, gradually enriching the representations until the final layer encodes the overall meaning of the passage. Finally, the model maps these vectors into a probability distribution over possible next tokens. By sampling from that distribution repeatedly, a transformer can extend text, answer questions, or role-play in dialogue. At the core, everything relies on deep learning, a field of machine learning where models with billions of parameters are trained on enormous datasets. Unlike early AI, which depended on hand-coded rule, deep learning adjusts its parameters automatically through backpropagation, tuning outputs to match training examples. Inside, it all comes down to arrays of numbers, tensors, and lots of matrix multiplications. Take GPT-3 as an example. 170 billion parameters, structured across tens of thousands of matrices. Two of the most important are the embedding matrix, which turns tokens into vectors, and the unembedding matrix, which maps vectors back to vocabulary probabilities. A crucial step is the softmax function, which converts raw numbers, called logits, into probabilities. By adjusting the temperature setting, we can make outputs more predictable or more creative. Low temperature keeps results safe and consistent. Higher temperature allows for variety, but risks incoherence. Word embeddings themselves capture rich relationships. For example, king minus man plus woman equals queen, or countries gifted to their capitals. These embeddings evolve as they pass through each layer, absorbing context and refining meaning. One limitation is context size. the maximum number of tokens a transformer can consider at once. That's why earlier models often lost track in very long conversations. In the end, almost all of the computation is giant matrix vector multiplications, guided by learned weights. And yet from this math emerges the ability to generate text, create images, or even compose music. The beauty is in the simplicity. Tokens, embeddings, attention, feed-forward layers, and softmax. These are the universal building blocks behind every transformer model. In the next videos, we'll dive deeper into the attention mechanism, the heart of transformers, the structure of feed-forward blocks, training methods, and more background on deep learning itself. With this foundation, you'll start to see how what looks like statistical prediction can actually feel intelligent.